Hello everyone, my name is Yating Zheng. Today I'm going to talk about swarm construction coordinated through the building material. In previous work, swarms of building robots have been coordinated through imagery, while the observations of previous construction trigger further construction actions. We call this kind of approach a standard algorithm. However, robots have limited perspective of the construction and need information about the structure. Therefore, it's very difficult for the builders to keep the structure in a valid state. In this case, we are going to consider about another algorithm called the block algorithm, where the intelligence that coordinates construction has been moved into the building material. In our swarm robotic construction system, we use the BuildBot to assemble the blocks by its manipulator. And the building material is the symmetry blocks. The symmetry blocks have the microcontrollers, which is used to make a decision and cope with information. It also has 6 faceboard. On each faceboard, we installed the NFC to communicate with its neighbors. And on each faceboard, we have LEDs which can light different color like blue, green, purple, and red. In our block algorithm, we have in the first place, we have a root block takes the lead, which decides which blocks are missing in the structure. Take the hardware experiment as an example. In the first place, the root block light purple on the side faces to show the buildbot that the blocks are missing on the side faces. So when the child blocks are connected to the structure, it will receive the information from its parent block, and it will decide where the blocks are missing after it by also lighting purple face. So when all the child blocks are assembled, the root block will light red to show that the structure is completed. Today we are going to talk about the 3 kind of experiments. The first one is the dynamic construction path. Using the standard algorithm, the buildbots only rely on its own local perception of the structure to trigger further construction. However, if we want to finish a structure, like figure C shows, we want two blocks get assembled on the top layer, either left or right, or front or back. We don't want the blocks attached to the left or front or back and right. However, with the local perception, the local pattern for the build-bots is always the same on each side. In the standard algorithm, the local perception for the build-bot is always being green, yellow, and green, and it's similar on each side. So in this case, it's difficult for the build-bot to decide which 2 blocks are assembled to the structure. However, with a hybrid algorithm, which is a block algorithm, we are able to solve this problem by lighting. In the first place, the structure light is lighting 4 building sizes yellow to show that the build-bot is able to build 1 block on the top. On the second place, when the block is attached on one of the building sites, the structure is able to detect it and disable another construction path, and save the corresponding building site as yellow to guide the build-bot. So in this case, the build-bot could place the final block in the correct location to complete the structure. Here we by executing the experiments with different numbers of robots, we could see that with the increase of the number of robots, the construction efficiency could also be improved. The second experiment is guided construction. In the standard algorithm, the block is has no ability to change its color by itself, and also it cannot communicate with the neighbors. So it can only change its neighbor. It can only change its color by the build-out before get attached to the structure. However, in the block algorithm, the blocks in the structure is able to communicate with the neighbors, and it can also light a different color automatically. And in the block algorithm, we can use the blue color to show that the nearest building site is on the left, and the red color means the nearest building site is on the right. So in this case, the structure could guide the builder to find the nearest building site, and thus to improve the construction efficiency. Here is the simulation about the guided construction using the block algorithm. So in the first place, the robot attaches block to the top of the leftmost block, and the illumination pattern is updated by the root block, and robot searches to the right for possible construction sites. And in the end, the robot attaches the last block to the top of the rightmost block. So we use both types of algorithm to finish the different lengths of structure. From the distribution of time taken to construct the short and light structures using different algorithms, we can see that using block algorithm, the time to finish the structure is always shorter than the standard algorithm. The third one is the flexible construction. So in the standard algorithm, the builder could only assemble the structure by its behavior roles. So for their users, they have to take the burden to design different behavior roles for the builder, and also make sure that the roles has no confliction with each other. So in this case, if we want to finish the structure like this, so in the first place, the root block, the builder could place one block in the middle. In the second place, when the builder comes in this way and see that there are two blocks, there are only one block, it will put another block on the top, and the structure will go in this way. And we have to notice that in the standard algorithm, the order of the block get attached to the structure should be very very serious. They cannot make the intermediate construction state conflict with each other. However, with block algorithm, we can finish it by the builder in any order. Here's the hardware experiment. Here's the simulation experiment about how the structure finished by the standard algorithm. First, the builder will put one block on the top, and then when the builder comes in another way, it will perceive that the structure is made of two blocks, and it will put another block in the front. The third step is that when it sees there are three blocks organized in this shape, it will put another block in the front. However, with the block algorithm, we can finish the experiment in a very short time. In this case, we can use 3 builder bots, which will recognize 3 building sites at the same time, and it can assemble the blocks into the structure at the same time, or in any order. It doesn't matter. So here we want to talk about the fault-tolerant survival swarm robotic construction system. So there are 2 types of fault conditions that we can solve using the block algorithm. Here is the case in the simulation to show both cases of fault tolerance. So the first one is that in dynamic construction paths, when 2 construction paths are selected by the 2 builder bots at the same time, the structure is able to detect one building construction site, and disable another construction path. So the one, another block in the structure could be removed by the buildbot. Another one is that due to the recognition fault or any other error in the buildbot, it could be occasionally put another block on the corner of the structure, not in the middle of the structure. So in this case, the structure could also detect that the unexpected block is attached on the structure and disable the structure into black. So the buildbot could also recognize the block is unused one and removed from the structure. So in this way, the structure could be finished as expected, even there's some fault conditions. Okay, thank you for listening, and I'm open for any questions.